Here we're going to go through practice set 7, where we get some practice doing nearest neighbors models and regularized regression models. So there's a bunch of setup that you have to do in order to complete this activity. And the first thing that I'm going to do is to define some of these custom functions that have been written specifically for BAS 474. The first one is scale data frame, and that's going to allow us to do automatic scaling of a data frame, which we know we need to do for nearest neighbors and regularization. And so I need to highlight the entirety of that function and just run it so that that function gets defined in the environment. And I'm going to do the same thing with suggest transformation. That's going to be a useful function to figure out, all right, if we want to transform variables to symmetry, what should we be doing? Taking the log, taking the square root, etc. Convert back categorical is not something that we're going to be using in this activity, but it's useful for taking a column that is a categorical variable and replacing it by a set of indicator variables. So one thing you want to make sure of is that you have R version 3.4.3. Most likely you do. You can just restart R and open it back up to see if you do have it. If not, it's time to update. And the other thing we need to do is to make sure that you have the most recent version of kNN installed, not just from CRAN, but also from the developers themselves. So there's some additional instructions up on Canvas for making sure you have the DevTools package installed, and then you've installed the developer version from GitHub, the most recent version of kNN. That'll ensure that the most recent batch of tools is available to everyone and that we'll all get the same answers when we start fitting models. Alright, part 1 of the activity is exploring a model to try to predict something about whether or not a customer is going to make a purchase from a catalog in the next quarter based on some of their characteristics. So I'm going to load up the reg class library and the data set we want to be working with. And in this case, we're going to be predicting the column by. So here's what we know about the customers: the number of quarters that they've made a purchase so far in their history, the percentage of the quarters with purchase so far as well, the number of catalogs they've received, etc., etc. So some potentially useful information for predicting whether or not that customer is going to make a purchase in the next quarter. So let's start off by fitting just the vanilla logistic regression model, something that we did last week, with no pre-processing, no transforming, no scaling, just so we get a baseline. So what we need to do, of course, since we're doing predictive analytics, is to split our data set into a training set and a holdout sample. We'll set aside that holdout sample to the very end just so that we can make sure that our model is generalizing about as well as what we expected. So using the standard random number seed, let's go ahead and split the data into 75% training and 25% holdout. So once we've done that, then we just need to tell R how we want to be estimating the generalization error. And in this case, we're just going to do vanilla 5-fold cross-validation with no repeats. And so this is the fit control object that we want to create. Method equals CV instead of repeated CV because it's just vanilla cross-validation, and with a value of k equal to 5. Now, because this is a classification problem, we're predicting the probability of by versus not by and classifying the individuals accordingly. We need to also make sure that when we set up the cross-validation, we say class probs equals true. That allows it to do estimation of probabilities. So we'll define that object, and then what we're asked to do is to find the estimated accuracy when generalizing for just the vanilla logistic regression model. So what I'm going to do is I'm just going to call the name of the model logistic, and I'm going to have to run the train function. All right, what formula am I going to be using? Well, I put what I want to be predicting, which is the by column, and we're just going to be using all predictor variables in our model. So by twiddle dot lets us predict it from everything. Now I'll always predict it on the training data. That's where I always fit the models. Not the entirety of the data set, not the holdout sample, always the training data set. And we need to say what method we're going to be using. GLM is the logistic regression model. And I'm also going to make sure to do the set seed 474 immediately before this. Now here is where I have to think, okay, is there more stuff that I need to add to this command? And so this is why I have the cheat sheet that is going to accompany every unit. The cheat sheet goes over in quite some detail about exactly how you fit all of these models. So I'm going to go down to the vanilla linear or logistic regression and just confirm that, okay, did I actually, am I fitting this model correctly here? All right, so in this case, if I want to be gauging the model based on accuracy, here's how I run it. If I want to be gauging the model on AUC, this is how I run it. I actually have this additional argument that I don't need. Now I'm sad that I have that included in the cheat sheet that I posted, but for just vanilla regression, we don't have to say how to tune it. So we just need the method, and we need, all right, how are we estimating that cross-validation? So I'll go back over here and just say, okay, TR control, the way you're going to train it, fit control. All right, so we run it, and then as it's running, I'll go ahead and just print out the name of the model, and we see that the estimated generalization accuracy is about 62%. So the estimated generalization accuracy is 62.1%. If I wanted the standard deviation associated with that, how close we think we've nailed that down, I can always get the results component of that object and let us know that it's about plus or minus 0.2%. So with SD of 2.2%, let's just keep track of that for now. And I'd like to know, is this higher than the naive model's accuracy on the training data? Well, how do we know what the naive model is doing? Well, we can just literally take a table, a frequency table, of the column we're trying to predict on the training data. We look at the majority, and in this case, the majority is the yes class. So the accuracy of the naive model just says whatever the majority is doing, everyone's doing. Let's just see what fraction are equal to yes, because that's what the naive model is going to predict for everyone. And we see the naive model gets an accuracy of 54.5%. So the naive model on the training data gets 54.5% accuracy, and that's our best estimate for how well it's going to generalize as well. So it looks like the estimated generalization accuracy of the vanilla logistic regression model is much higher. So it looks like we stand to gain something by trying to model the probability of buying versus not buying based on some of these predictor variables. Naive model says nothing that we've collected has any information about this. Logistic regression says, nope, we do have some information. We'll model that probability with a logistic curve. Okay, question number 2 asks us to explore transformations to symmetry. Because very often when models in data mining and models in data science work with symmetric predictor variables, the models tend to prefer better. Not always, but most of the time they do. And so that's worth exploring here. So how do we know what transformation to employ? Well, we have to go through systematically each one of the numerical predictor columns and see how we can best transform to symmetry. And this is best done manually one by one. I do have a for loop in the cheat sheet that'll speed things up, but it's always better, if we have the time to do it, to do this one by one. All right, so let's go ahead and take the original data set and let's left arrow that into catalog.trans. And let's modify the contents of catalog.trans so we don't destroy the original data. One thing to note is that you're always going to be choosing what transformations to use on the entirety of the data set. We'll fit the model on the training data set, but we want to decide what transformation on the entirety of the data set. And then we'll split into training and holdout once we've decided on that. So the second column is quarters with purchase. So let's take a look at the distribution. Very skewed, so maybe we would do better if we transform to symmetry. And that suggest transformation function that we defined earlier that's built into this data file, it's not a part of any sort of data package here. We're going to say, all right, let's try out sequences of transformations, raising it from the -3 power up to the +3 power in increments of 0.5. When we try out 0, that's the log 10. And so let's just see what this suggests. It says, okay, well, let's try raising catalog.trans, the second column of that, to the second power. And that's just the square root, but I'm going to go ahead and just manually say, let's raise that to the 0.5 power. So what I'm going to do is I'm going to slightly change up the syntax here. Let's take the original values in the second column, raise them to the half power, and left arrow that into the second column of catalog.trans. And let's see, okay, do we get a more symmetric distribution? Kind of. But that's what suggest transformation is suggesting, so we'll just go with that. We'll just go with suggest transformation, what it's saying. All right, so now we just got to methodically go and do this for each one of these numerical predictor variables. So we see we have to look at column 3, 4, 5, 6, and 7. So it's just a bunch of copy and pasting. 2, 3, 4, 5, 6, 7. It's tedious, but it pays off in the end. So we'll go ahead and look to see what about this third column. Yeah, pretty skewed here. What does suggest transformation? All right, taking the square root once again. Well, that's pretty easy. Let's replace the values in the third column with the square roots of the original values, raising it to the 0.5 power. How's that look now? Well, maybe an improvement. We're not sure. We'll just go with what suggest transformation is giving us. All right, so the fourth column here, let's see how we're going to modify these contents. What do we start out with? Very skewed right here. Let's see what the transformation we should be using. It suggests log 10. So I'll take log 10 of ex7.catalog, the fourth column there. And how well do we do after the fact? Well, maybe a little bit less skewed. Very rare are we going to find transformations that exactly achieve symmetry. We just try to do as good as we can. So very skewed here for the fifth column. What does suggest transformations suggest? It says take the square root once again. So we'll take the square root. Let's look at the results. And we're definitely looking more symmetric than where we started out. Still some skewness, but suggest transformation says that this is pretty much the best that we can do. Now the sixth column, you get the idea. It's just a bunch of copy and pasting and changing numbers one by one. Pretty skewed. Transformation says, oh, well, let's raise this to the minus 0.5 power. So, okay, no problem. Just take the original values, and when we put the power sign, we'll just change this to minus 0.5. And we'll take a look. And a bit more symmetric, so pretty happy with that. And then finally, the very last column here. Let's see what we're starting out with. Very skewed. What does suggest transformation say? It says to take the log. So let's replace the values that were originally recorded in ex.7 catalog here into the seventh column of catalog trans and look to see how well we did. A bit more symmetric. Now, one thing to note is that you can only take the negative power of something in the log if every value was positive and actually greater than 0. We can't even have any zeros. So one thing we should have done before doing all this transformation is to see, okay, well, could we have taken the log and the negative or 1 over the square root of these things here? And the suggest transformations is actually built in to guard you against doing illegal transformations. If there are zeros, like what we see here and what we see here, or negative values, it's not even going to try out the log or any sort of negative powers. So we'll just stick with what suggest transformations said we should be doing. Do we recover what we should have done based on what the activity suggested? Going through column by column and just double checking. Yeah, it looks like that we are doing the set of transformations that we expect. All right, so that's pretty tedious one by one. It's the best way to go about doing it because that way you can make a decision on, all right, I could have just stuck with the original values, or, oh, it's really a good idea that I'm making these transformations. How can you do this efficiently with the for loop? Well, let me show you. All right, so let's go ahead and actually overwrite catalog.trans, all that hard work that we just did, and let's get this for loop working for us. So way back up in the cheat sheet, it goes through an example of how you would go and write a for loop to accomplish this efficiently. So strategy 2, using a for loop to automatically select transformations. Let's go ahead and copy and paste this back in here and change what we need to do. All right, so we've already made a copy of the original data and put it into catalog.trans. That's what we need to start out with. And the for loop is going to go through every single one of the columns one by one. So we'll go through all the columns in the original data that we have. And what this is doing is it's running suggest transformation on column I. So we'll take the original value or the original values in the ex7.catalog data frame. It's trying out powers from -3 to 0.3 and increments of 0.5. And add equals 0 just says, okay, don't add anything to these quantities before trying the transformation. We'll keep that as the default. In this case, because we did see some zeros in the data, it might be smart to add in, say, add equals 1, but we'll just keep it as 0 just for illustration here. All right, so for each column, we see what the best transformation is. If it turns out that trans is equal to null, which it will if it's a categorical variable, it just skips on to the next column. If trans is log 10, well, we make the transformation of the log 10 transformation. So catalog.trans will be equal to the log 10 of the originally recorded values. Otherwise, we'll take those values and just raise it to the power that's suggested. That's going to be contained in trans. So here we go. We can run the entirety of the for loop. Some additional stuff, what's this doing? Well, sometimes when we're predicting a numerical response, we actually don't want to do those transformations. And so we'll need to replace the transform values with the original values. So in this example, if we had gone through systematically and whoops, we transformed sold week 13, a numerical column, we might want to replace that with the original values. In this case, we're predicting buy versus not buy, so we don't need to worry about that. All right, do we recover what we should have been recovering? Just a quick scan through shows us that, yep, looks like we have the transform data. All right, question number 3 asks us to remake the training and holdout samples, but with the transform data. We'll call them train trans and holdout trans here and fit the vanilla logistic regression model with no other processing. All right, so does transforming help us out? All right, well, here's the fit control object that we need to set up. It's the vanilla cross-validation, just k equal to 5. And the way that we make train trans and holdout trans is just by working with that catalog trans. So we'll split that into training and holdout. Remember, all that transformation, any sort of scaling, takes place on the original data. Then we split it up. And now let's go ahead and fit that model. Now I'm lazy, so I'm going to go and actually just take the code I'd written for the logistic regression model. And I'm just going to change some of the names of this. So I'm going to call this logistic.trans to make it clear that I'm fitting this on the transformed version of the training data. Nothing else really needs to change, so I can fit it. And then I can say, okay, well, how well do we do? I don't need anything about the naive model. Naive model doesn't change. And here we go. So on the transformed data, the estimated generalization accuracy is, what do I get here? 62.4%, just rounding to that. 1SD is 2.2% once again. And we're asked, all right, does transforming the predictor seem to improve the generalization of the model? Well, how well did we do? Well, back before it was 62.1%. I can print that out once again because it's already stored here. And so I see that, just comparing those numbers outright, I'd see a hint that maybe it would increase the performance, but these are definitely within one standard deviation of each other. So I can't make it a definitive conclusion either way. A little bit of evidence suggesting transforming helps, but, this could have just been a happy accident here since they're within one standard deviation. So transforming may or may not help out the accuracy without transforming the estimated generalization at 1%. So transforming yields a slightly higher value, but this is within one standard deviation, so it's not definitive proof that transforming is better. All right, so it might help out, but based on the analysis, we can't say for sure. Most likely, if we had to choose between both strategies, we would pick the transform data because we do have just a little bit better of a performance, but we're not compelled, based on the analysis, to go with that transformed method here. All right, question number 4 says that scaling each variable often, but not always, improves the results of logistic regression models as well. So let's do some investigation. We're going to make 2 additional data frames, catalog scaled, where we just scale the originally recorded values, and catalog.transscaled, which is the scaled versions of the transformed data. So luckily, scale data frame here is there to help us out. So what we can do is just immediately define catalog scaled as the result of running scale data frame on the originally recorded values. So boom, we got that. Catalog.transscaled can be recovered by just running scale data frame on the catalog trans data frame that we had made. So remember, all that pre-processing happens before the split into the training and the holdout. So, all right, we've made the scaled version, but no transformation, and we've made the scaled plus transformed, or yes, transformed then scaled versions as well. And now we got to split this up into training and holdout. Well, we've already defined the train rows, so it's really just as simple as kind of borrowing some of this stuff before and just renaming things. So train.scaled will be the train rows of the catalog.scaled data frame, and holdout scaled will be everything but that. So split that up, and then finally train.transscaled will be the relevant rows of catalog transscaled here. So we got that. We see it's just a lot of copying and pasting here and just changing some of these words. It's kind of the nice thing. Once you've done this a few times, you get the hang of it, and it works out pretty fast. All right, so now we have 4 versions of the training data in the holdout sample: the raw values, the scaled but untransformed values, the transformed but unscaled values, and the transformed values then scaled. Now, we never know what's really going to work ahead of time, and we just try everything out and see, all right, what happens to have the highest estimated generalization error. Maybe we'll go with that version, or if we have compelling evidence to go with the lowest error, we'll make sure to go with that. Or we could choose something with the 1 standard deviation rule. So it's saying to fit the logistic regression models to see the estimated accuracies when generalizing. So, all right, let's do that. So we've already set up the fit control object, so all we need to do is kind of borrow this code. Let's call it logistic.scale, and we'll fit this on the scaled version of the scaled version of the training data, and then finally logistic.transscaled, and we'll fit that on this transformed then scaled versions of the training data. Whew, a lot of stuff that we're juggling around. And let's take a look. Let's look at the results components of both of these fitted models. Okay, so scaled only gives an estimated accuracy of 62.1%, and the transformed then scaled version gives an estimated accuracy of 62.4%. Looking back up, what we would found is that just transforming also gives 62.4%. So scaling after that transforming didn't really change anything. And then also what we saw is that just on the raw data, we started out with 62.1%. After scaling, we also have 62.1%. So there's actually no change here in the accuracy once we scale. So in this case, scaling didn't help us out whatsoever. Sometimes it does, sometimes it doesn't. We try it out and just kind of see. So there's no change in accuracy when going from the raw to scaled values, nor is there a change in accuracy when going from the transformed to the transformed plus scaled version. So it doesn't look like scaling helped us out at all in this example. Sometimes it does, sometimes it doesn't. You never know ahead of time. All right, so we have a pretty good feel over what vanilla logistic regression can get us in terms of generalization accuracy, about 62.4%. Perhaps regularizing the model is going to help us out. So fundamentally, logistic regression is choosing the coefficients of the model in the wrong way. It's solely focused on minimizing the bias of the model on the training data, and we know that the estimated generalization error of a model depends on the bias, smaller is better, but there's the variance component of the model building procedure as well. So the variance component is measuring how stable the model is if it were to be fit on a different set of individuals. So how much does the model's form change if we used a different training set? The more it changes, the higher the variance. The other thing that it's getting at is it's kind of measuring how much information it's extracting from the individuals in the training data. If you don't extract all that much information, you'll have a very low variance model. Turns out the form of that model is not going to change all that much if you use a different set of individuals, because you're not really using much information from them anyway. It's not very sensitive to that set of individuals in the data. If you extract a lot of information out of the individuals in the training data, well, your model is very sensitive to the particular set of individuals there, and so your models can have a fairly high variance. So regularizing a logistic regression model just means giving it a penalty based on how much information that you're extracting from the individuals in the training data. And it does so by penalizing the size of the coefficients of the regression model. So if we scale the data, then that means the size of the coefficients tells us how much information we're taking out of each of those predictor variables. So we'd like to get the coefficients as close to 0 as possible, meaning we're using as least amount of information as we can from the training individuals, while still fitting the data pretty well. So let's go ahead and fit the regularized logistic regression models. Let's go over to the cheat sheet to remind us how we do that. Now, with a regularized regression model, we need to actually determine two different parameters, this parameter called alpha and this parameter called lambda. Lambda is telling us essentially how much we're going to be penalizing the model based on the amount of information that it's extracting from the individuals. Alpha is going to essentially give us a mix between the two different versions of regularizing, the lasso and the ridge versions. So we don't know what's going to work ahead of time. We have to try a bunch of values out and see what ends up working. So alpha is always going to be between 0 and 1, so we can start out a search just by going from 0 to 1 in increments of 0.1. Lambda, we might want to be a really small value, so basically hardly at all penalizing it based on the amount of information extracted from the data. Or maybe lambda should be a really big number. Maybe we should give it a really large penalty about the amount of information being extracted. So for lambda, generally our search is going to be 10 raised to a sequence of powers. And in this case, we're going to go from -5 to 2. So values of lambda we're going to try out range from 0.00001 all the way up to 100. So if we run this expand.grid command, we'll see all the different combinations of alpha and lambda that we'll be considering. So we see we're actually going to try out 220 different models. Let's go ahead and left arrow that into glm.net_grid. And because we're working with the accuracy, here's how we fit the model. So in this case, we're predicting by. And in this case, we're doing this from all 4 versions of the training data. So, all right, we'll stick with data equal train. The method is glm.net for regularized regression. I've already set up that fit control object, and here's our tuning grid. So glm.net_grid tells us the combinations of parameters we'll be looking at. So since we're fitting 4 models, we can do this glm.scaled, glm.trans, and glm.net.transscaled using the relevant version of the training data. All right, so let's fit all these guys. Boom, 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 boom. And what we'll be doing is looking at the estimated generalization error. Since we've fit for each one of these training versions 220 different models, it's kind of nice to just look at the parameters that happen to have the lowest estimated generalization error, and that's what the following 3 commands is going to help us out with. So on the raw data, the training version of that, we see that, wow, a lot of output here. So for each combination of alpha and each combination of lambda here, it's giving us the estimated generalization accuracy along with the 1 standard deviation. Too much stuff to really search through. The $best tune tells us it looks like the optimal values of alpha is 0.8 and 0.206918. So I'm going to go ahead and copy that here because that's what the raw data was telling us. And it looks like that estimated generalization accuracy, well, if I run this command right here, this just extracts the row of the results component associated with the best tuning parameters. We see the estimated generalization accuracy is this number right here, a little bit above 62%. Okay, so let's go ahead and, ignore what those previous 2 commands are. Let's just look at the best row of those results here. So I'm just going to replace the name of these models in the relevant commands. so that I'm just looking at the best fitting model for the scaled version, the best fitting model for the transformed version, and the best fitting model of the transformed plus scaled versions. So all right, for the scaled version, we see that alpha is still 0.8. Lambda in this case, well, it's still this number here, so that's easy. We can just copy and paste that. The estimated generalization accuracy when we scale the data looks to be the same as if we had not scaled it. So I can just borrow this number right here. What about on the transform version? Well, alpha now is suggested to be 1. Lambda, still the same number actually, and the estimated generalization accuracy, a little bit higher here. Transform plus scaled, alpha of 1, same value of lambda, estimated generalization accuracy, still the same thing. That's convenient. And there we go. So we've regularized the regressions. We've tried out on the 4 versions of the training data. And what we see is that regularization seems to help out a little bit, especially if we work with the transformed versions of the data sets. Now in this case, everything is still within 1 standard deviation of each other, so all right, we're not that impressed by the performance of regularization. But without regularizing, we saw that when we worked with the transformed data, the estimated accuracy was 62.4%, and it looks like that bumps up slightly to 62.9% or so. Still within 1 standard deviation, but maybe we are getting a little bit of a performance increase. So have we done what the question suggested? We fit the 4 models and we filled in the table below. So there we go. We went through 220 different models for each version of the training data set. So really 840 models, 880 models. It's a lot of stuff to go through, and we've kind of selected the best candidates here. All right, question 6 says that although the models examined have estimated accuracies within 1 standard deviation of each other, so literally every single model that we've tried actually seems to be acceptable from the viewpoint of that 1 standard deviation rule, let's go ahead and just stick with the model that had the highest estimated generalization accuracy. So in other words, the one using the transformed but unscaled data. There's no difference between scaled versus unscaled in this case, so we'll go with the unscaled version. I'm just pointing you towards that one, I guess. So out of curiosity, let's just see how well the 4 models do on the holdout sample for these regularized versions. So let's find the accuracy of the 4 models on the holdout sample, see if any are overfit, and we'll see if we would have made the right decision. So any model would have been the correct decision in this case according to the 1 standard deviation rule. If we say, well, I'm just going to go with this particular version, transform plus unscaled, that did have the highest estimated generalization accuracy, I can see if I happen to have made the right choice. Now, I'd never, ever, ever, ever change my decision based on the performance on the holdout sample. That's not the job of the holdout sample, but it satisfies my curiosity. All right, so how do we make predictions on the holdout sample? Well, it's all in the cheat sheet here. Let's go ahead and, because we're doing classification and predictions here, borrow this code, and let's talk about this. So predict is the name of the function. We say what model we want to be making predictions on, and then we want to say what data set are we going to be using to make predictions. We want to be making predictions on the holdout. So in this case, I'm going to call this pred.raw because we're using the raw versions of the training data for the model name GLMNet. So if I run this, let's just look to see what I get out. So these are the yes/nos. And so I can get the accuracy by just looking at the average value of the following vector. Take pred raw and ask whether or not this is equal to the values in the by column of the holdout sample. This will either be true or false depending on if they match up or if they don't. And if I ask for the average value of that vector, that's going to give me the proportion that are true, or in other words, the accuracy of the model on the holdout sample. So 62.6%. All right, now let's go ahead and just use all of these guys here. We can fit this for all of the different models. We had glmnet.scaled. So let's go ahead and do pred.scaled. We can use the original holdout sample because what's by and what's not by isn't changing based on our transformations or scalings. And I'll go ahead and just call this trans and trans scaled. glmnet.trans_scaled, glmnet.trans. Whew, a lot of stuff going on here. So, all right, let's make predictions from the scaled version of the original values, but non-transformed. Oops. That's weird. Why would that give such a low accuracy? All right, I need to investigate that, but let's go and do the pred trans now. Predictions on the transformed but unscaled. And all right, so let me pause this and investigate. So here's my error. Probably one that you guys will make too, so you see even after doing this for 15 years, I still make mistakes all the time. I used the wrong holdout samples to make predictions on. So I need to be just consistent with, okay, where was this data actually fit? If you fit it on the scaled version of the transformed data, you need to be using the holdout sample on the scaled versions of the transformed data as well. So we're going to use holdout trans scaled, we're going to use holdout.trans, and we're going to use holdout.scaled because we're using the model that was on the scaled version of the data. So let's go through this once again. 62.6% on just the raw data, 62.6% if we just scale but don't transform. If we just do transformations, no scaling, 63.2%. That's the one we had picked, by the way. If we do transformation then scaling, we get 62.6% here. All right, so in this case, we happened to make the right call, but we super lucked out because there really wasn't literally no difference between the estimated accuracy on the transformed and then the transformed plus scale data here. But it turns out that it looks like this is the model that lucked out and did the best here. So, all right, let's delete that stuff. We don't need it. And the model built on the transformed but unscaled data happens to perform the best on this holdout sample. A different holdout sample, we might have had a different story here, with an accuracy of 63.2% versus 62.6% for the three other models. So none of the models look to be overfit because their actual errors on the holdout are about the same as what was estimated. So as long as they're not, the accuracy is not 10% worse, we're pretty happy. And in this case, these estimated accuracies are all like 62% or so, and we're getting there on the actual holdout sample. So we're doing good. Nothing's overfit. And we also answered this last question, almost guaranteed to be an exam question. We never change which model we have selected based on performances on the holdout sample. That holdout sample is literally just a sanity check to make sure that our final selected model has about the same generalization error as what we expected. Okay, question 7a now asks us to switch gears and consider the k-nearest neighbor model. So the philosophy is that individuals with similar characteristics, similar x values, are likely to have similar values of y as well. That's a reasonable assumption. The k-nearest neighbor model might do pretty good here. So one thing we have to worry about is what version of the data do we work with? Do we work with the raw values, the scaled values, the transform values, or transform plus scaled values? Well, we've already made these 4 data sets, so let's just try out everything and see what happens to work. So in this case, we don't know how many neighbors we should be using ahead of time. Maybe 1, maybe 5, maybe 10, maybe 50. So let's go ahead and set up kNN grid to consider all values of k from 1 to 40. All right, so how are we going to fit these models? Well, very similarly to how we fit the models before. The only thing we're changing is the method. kNN for k-nearest neighbors, glmnet was for glmnet here. So let's go ahead and just kind of copy and paste this stuff. So we're using all 4 versions of the training data that we have generated. So just the scaled, just the transformed, and then the scaled after transforming. And let's give these the appropriate names as well. And once we've done all this copy and pasting, changing the names around to what we want them to be, we can set it loose to see how is nearest neighbors doing. So a very easy model to fit. It's literally the same syntax and everything, the same formula that we've been using for the other models. We just have to make sure that we're using the right training data sets. They're all k nearest neighbors for method. We've set up the kNN grid to consider values of k from 1 to 40, and the fit control object we defined a long time ago that talked about how we estimate that generalization error, just vanilla 5-fold cross-validation in this case. The important thing is, of course, having that set seed 474, or whatever number, on the same line as train because it's a random procedure. We need to make sure we get the same set of results. Alright, so which model are we going to choose here? What value of k and what type of preprocessing would we choose? Well, let's take a look back here. So on the raw data, 61.7%. On the scaled version of the raw data, 62.2%, a little bit better. On the transformed but unscaled version, 62.6%. And on the scaled data after transforming, 62.3%. So once again, these are all within one standard deviation of each other. There's no compelling reason to go for one versus the others. So typically, unless we have a reason to do so otherwise, we'll just go with the model that had the highest estimated accuracy. So the model I would select would be the 32 nearest neighbor model. Notice 32 because that's where it's at right here. On the transformed but unscaled data, because that happened to have the highest estimated accuracy. However, all of the models considered have estimated accuracies within one standard deviation, so any of them would be an acceptable choice. All right, 7a follow-up asks us to make a cool plot here. So we can actually see how the generalization error is tied in to our choice of k, the number of neighbors we're actually using. Let's actually go ahead and reuse this code here. On the kNN.trans results data frame, if we print that out, we see here's all the cool information, the choice of k, the estimated accuracy, the one standard deviation, etc. This is a data frame, and we can make a scatter plot using these as the column names. So let's plot how the accuracy changes versus the value of k in this data frame. And we see, okay, as we increase the number of neighbors in our model, this estimated accuracy is sizably increasing here up to a point. This is where that 32 was, that happened to peak out. And then if we use too many neighbors, it looks like that our model is not doing as good. So there is a sweet spot in terms of the correct value of k here, and k equals to 32. Looks like a reasonable choice. All right, let's make predictions for all 4 models on the holdout sample and see if our selected model, transformed but unscaled, actually does happen to perform the best, just out of curiosity. So here's where I want to go back and look at how that k nearest neighbors model was doing predictions, because when we do predictions for the nearest neighbor model, we actually have to set the seed again. And that's because we might have ties. If we're using a 32 nearest neighbor model, what happens if 16 say yes and 16 say no? Well, in that case, R actually just flips a coin to break that tie. And if we want to make sure to produce the same set of predictions so we can check our answers, we have to make sure that the same set of random ties are split in the same way here. So what we'll do is this set seed 474. Once again, we're going to predict from the fitted k nearest neighbors model. What do we name it? Going back up here, we named it kNN.raw, and we're making predictions on the holdout sample. So we get our yeses and nos. And so what I'm going to do actually, since I already took the time with the regularized regression models where I was doing all these predictions, I'm actually going to just take that code and put it down here. Make sure the set seed is on the same line as everything with predictions. So some copy paste action here. Get this all set up. I'm not going to change the name of where I'm saving these predictions to. I'm just going to change the name of these models. So we started out with kNN.raw. Then we moved on to kNN.scaled. Notice this is a smart move on this case because I need to make sure to be predicting on the holdout scaled here. And then we moved on to kNN trans. And then finally we moved on to kNN.trans_scaled. Is everything set up right? All right. Model fit on the raw values, raw holdout. On the scaled versions, predicting on scaled. Model on the trans data, holdout trans. Trans then scale data, holdout trans. Looks good. So let's go ahead and see, drum roll, how well each of these do. Well, here's kind of a shocker. Not really a shocker because this happens all the time. Our selected model here, the k nearest neighbors model with k equal to 32, fit on the transformed data but unscaled, actually performs the worst of all four models that we're looking at. And so we're kind of sad about this because, we'd like to always be making the right choice, but we're never really going to know what's going to perform the best on brand new data. That's why we just estimate the performances of a bunch of models and go with what we think might be best. On some holdout samples we'll be right, on other holdout samples we'll be wrong. Here we see that we actually picked the worst of those four models for this particular holdout sample, but there was no way of knowing about that ahead of time. We did our best. Do we use this result to change the model we selected? Well, of course not. We never use the holdout sample to change or select a model. It's just as a sanity check to make sure our models aren't overfit. All right, so is the model that we thought was going to be the best actually the best? No. The model we thought was going to be the best, the 32 nearest neighbor on the transformed but unscaled values, actually performs the worst of the four models on this holdout sample. But of course, we don't change our selection. This was just out of curiosity that we are comparing the models. Okay, but none of them look like they're overfit because that estimated accuracy, the 62% or so, is pretty close to what the actual accuracies turned out to be. So 10% of 62% gives us like a 6% buffer. So as long as, we're not getting these actual accuracies on the holdout that are like 56% or lower, then, our model doesn't really have much evidence that it's overfit. So we do take a performance hit when we start trying to use this model on brand new data, but it's not that big of a hit here. Okay, so question number 8 says, so what are we going to select as our final model here after all of this analysis? Well, how do we select a final model? Well, we go back and we look at all of the estimated generalization accuracies of every single model that we've considered so far, and we choose our favorite. So the one standard deviation rule can help narrow down acceptable decisions. And in this case, if you remember, this was the model that had the highest estimated generalization accuracy of the nearest neighbors models, 62.6%. And if we look back to the best regularized version, 62.9%, but these are all within one standard deviation of each other. So the upshot is, I don't need to run any code here. Basically, every model we have considered so far is within one standard deviation of the model with the highest estimated generalization accuracy. So literally every model here is an acceptable choice, but why not go with the model with the overall highest estimated generalization accuracy, and that would be either the regularized logistic regression on the scaled or on the transformed or transformed scaled versions of the training. All right, so that was kind of our verdict. That was the highest that we were able to find, and so, we'd probably end up going with that. I'll change that into a 1. All right, so part 2 of the activity asks us to change gears once again and to compare regularized regression models, but now when we're predicting a numerical response. So we're trying to predict response rate in the census data, and it's pretty much just the exact same procedure over again. So a lot of copy and pasting, a lot of kind of tedious stuff, but all right, let's go ahead and work through it. So reg class is loaded, the census data is loaded. We're going to use 60% training, 40% holdout, split that with the random number seed, and let's make the train and holdout on the raw data. And once again, we'll do just vanilla 5-fold cross-validation. Notice there's no additional argument here. We're not estimating probabilities, so we don't need to turn on that option here. We can just define fit control this way. So once again, it wants us to create 4 versions of the training and the holdout samples. We've already created one, good for us. We have the raw data. Now we want the scaled data but not transformed, the transformed but not scaled, and the transformed then scaled data. Whew, all right, so let's do this. This actually isn't all that bad because we can make the census scaled version just by running scale data frame on the original data. So that part's done. We just have to make the scaled versions of the training and the holdout data. And that's pretty easy to do because we've already defined train rows, so we just need to extract those particular rows out of the scaled versions of the entirety of the data. Okay, so that part was easy. Suggest transformation says, okay, well maybe we should be using a transform version of the data values instead of the original data values. But in this case, it's not feasible to go through and look at every single one of these values one by one to see what transformation we want to be looking at. Let me load up that census data frame once again because I think I was looking at that wrong version. There we go. So 39 variables, we're predicting response rate. We're not going to go through one by one and say, should we be taking the square root or the log of each of these? We need some sort of automation to help us out. So once again, let's go back to that cheat sheet and see how this works. So to do this kind of automatic selection of the best transformation, let's copy paste this code and see what we need to do. All right, so we're going to be making census.trans, and we're going to left arrow that initially to be the original values. Now what we'll do is we'll loop through each column of census and we'll figure out the best transformation. So we'll look at the ith column of census, we'll try out the same values of these powers, and in this case if we scan down we don't see any negative numbers. We do see some zeros here, but we're not going to add anything to these columns. Whenever there's a zero, it's just going to automatically exclude logarithmic transformations or transformations where we're raising something to a negative power, and that's fine. So the rest of this code we can just pretty much run as long as we promise to update the names of these data frames that we're modifying here. So there we go. If it's the log transform, take the log. If it's not the log transform, we'll raise it to that power. So we'll go through each of these columns, done, super easy. And now actually, because we said to go through each one of the columns, whoops, we actually transformed response rate. That may or may not be the right thing to do. In this case, we're just going to work though with the raw values of response rate. Not too bad to actually look at because it's kind of symmetric as it is. We don't have to worry too much about doing transformations. So what I'm going to do is to replace what we had just overwritten in terms of with the transform values what the original values were. So I'm going to take census response rate, the original values, and left arrow that into the census trans response rate so that I have the originally recorded values there. Going through this for loop transformed every single one of the columns. Okay, so not too bad. And actually what's nice is that I can basically reuse this code now. Let's take out the train rows of census.trans to make the holdout.trans and the training.trans as required. And then finally, we want the scaled version after transformation. So we can make census.trans scaled just by running the scale data frame on our census trans. Got that in, and then finally update this code so that we make the training versions on the transformed and scaled values of census. All right, so we're good to go. All of those data frames are set up. 4 versions. What's going to work best? We never know ahead of time. We've got to try everything out. Okay, so part B says to fit the following models. Vanilla linear regression on the 4 training data sets. We'll ignore any warnings that come out. Regularized regression on the 4 training data sets using a whole bunch of combinations of alpha and lambda. And then finally, k nearest neighbors on the 4 training data sets as well. We'll set up kNN grid so that values of k of 1 to 40 are considered. So since we've already set up these grids, I'm going to go ahead and just borrow what we had written before just to speed things up a little bit. So there's my kNN grid. We'll go way back up to where we set up the GLMNet grid. All right, we're happy with that. And now it's just a matter of going through methodically every single one of these models. So copy and paste is going to be our friend here. Since we're going to be running train, set seed 474, train, what are we predicting? Response rate, what are we predicting it from? Everything, twiddle dot. What data are we predicting this from? Data equals train. And what are we going to use as our TR control? Well, we're going to use fit control. Fit control we set up all the way back up here. Let's make sure that was defined appropriately. So here we go. So what are we going to call this model? Well, we got to say what method we're using. Method equals GLM says vanilla linear regression here. So I'm just going to call this M. Why not? Let's go back to the BAS 320 days where we called everything M here. So this is on the raw data value. So I'm actually going to call this mRaw. We'll run it and we'll do some copy and pasting. Those are the warnings that I was mentioning. In a graduate level class, you'd learn why we're getting these warnings out, this rank deficient matrix, but the upshot is that we have a few columns that add up to the values of a third column. So urban plus rural equals to suburban. The different ethnicity columns add up to 100%, et cetera, et cetera. That's what's making those warnings. So we'll make a M scaled, we'll make an M trans, and we'll make an M trans scaled just by working with the appropriate versions of the training data. And there you go. So we have these 4 versions. They're fit on their appropriate set versions of the training data, and we get all these things out. All right, now for the regularized regression. All right, I'm going to use this code once again. I've already written all the set seeds. I'm going to change the name of these, GLMNet here. I like that for the name for my regularized models. So on the 4 different versions of the training data, notice that, okay, that's all set up correctly. The names match up with the names of the training data, but we're not using GLM, we're using GLMNet now. And the thing with GLMNet, though, is that we need to say what's going to be our tune grid. So what values of these parameters are we going to be trying out? What are the values of alpha? What are the values of lambda that we want to be trying? So I'm going to add that as an additional argument for each of these guys. These commands are getting pretty long at this point. We can run all of these guys. And while that is going, I'm going to copy and paste and go ahead and, well, now we got some warnings here. So response rate wasn't found. Did I split that up? All right, we have train and holdout. That's part of the census. We have the train scaled and holdout scaled. We have holdout trans and trans scaled here. So let me just run these models once again just to make sure that everything is good. Rank deficient is fine, we can ignore it. And we go ahead and run these. All right, so no error messages that says, hey, I couldn't find this variable. Let's just take a look at what some of these results are. Sometimes the model can't be fit, and so that's when you get these weird messages out. So not all values, not all combinations of alpha and lambda are going to be okay. So this is just letting you know when that was okay. And let me just verify that the response rate was the originally recorded values, just to make sure that all these are, let's see, I forgot to replace to go back and do that one more time. So scale data frame is going to scale even the y variable that you want to predict. So we need to make sure that we replace that in the appropriate position. So I forgot to do that in 2 places. That's kind of embarrassing. So census trans scale $ response rate is going to be equal to the original recorded values. Original recorded values. So let's go and try that again. And this is why it's nice to have all this code in these chunks. You see that even after 15 years, I still make mistakes all the time, so, don't be shocked or surprised or frustrated when you keep making mistakes. It still happens. All right, so we fit regularized and we fit unregularized regression. Now let's just do the k-nearest neighbors. All we got to do is change the name. I'm going to keep the .raw, .scaled, all that stuff. The only thing we have to change now is kNN. That's what we're fitting. Got it. Run it. Oh, not glmnet grid though. We need to make sure to say what values of k we need. So we got this. All right, so it's doing its thing. I hope all that code is working out good. As you can see, a lot of it's just copying and pasting. Make sure that you have the right object for TuneGrid. Make sure you have the right method, the right model type that you want to be using. Make sure you always got that set seed in the same line as train, and make sure that the model that you're fitting and you're naming appropriately is actually on that version of the training data that you're considering. As long as you can be consistent, it's a guaranteed recipe for success. All right, now when we go and compare the best versions of all of these different models here, we're going to borrow, once again, a line of code from up here. Actually, borrow a lot of lines from up here. So all we need to get out, and if we always use the same names for everything, this becomes a lot easier here. This is extracting the best model on the raw data, the scale data, etc. So we can just kind of see here the values of k for these different situations. Let's go way back to when we did the regularized regression and borrow some of that code as well. Extracting out the one row, the results component of our model names, the ones that have the best stuff right here. So that's there as well. It's looking nice. And then we'll just have to copy and paste this, and we'll just do, this is our M raw, M scaled, M trans, and M trans scaled. Get the names consistent. All right, so we'll go one by one now. I think I have to correct one of these lines of code as we go. So linear regression, raw data, estimated generalization error about 4.79. We scale that, 4.79. Scaling didn't do anything for us. If we transform the values, 4.78 with a little bit left over. Maybe a smidge better here, but not all that much. If we scale the transformed, no difference here. So it looks like transforming might have helped out just a little tiny wee bit. Let me make sure I have glmnet.raw, since that's what I called it. RMSE 4.788. All right, so it looks like on the raw data values, regularizing the regression didn't help all that much. Scaling doesn't change. On the transform data, well, it looks like we do just a tiny bit worse. Tiny bit worse here, same as if we didn't scale it here. What about nearest neighbors? Ooh, 6.7, not a great model. A lot worse than these others here. So if we scale, transform, we do better than if we work just on the raw data values. That's almost always the case, but we see that these models just are not competitive whatsoever with the regression type models. So which of these 12 models seem acceptable and which do not? Which was you selected your final model? So all versions of the regression models, regularized or not, are acceptable. They all have an estimated error within 1 standard deviation of the best. The kNN models are clearly inferior with an estimated error way more than 1 SD above the errors of the regression models. So steer away from those nearest neighbor models. What would be the overall best choice? Well, it's up to you. Let's just scan through once again. 4.79, 4.79, 4.786, 4.788, 88, 83. Do a little bit better. That's the best seen so far. And that's not going to matter all that much either. So it looks like, let's go with the model that had the overall lowest error, which is the regularized regression on the transformed data. That's what I would end up doing without any other compelling reason to choose something else. They're all within 1 SD of each other, but typically we just go with the overall lowest. All right, part D says produce a list of the variable importances, at least according to the regularized regression on the scaled and transformed data. So what's important and what's not here? So let's take a look. We get a list. The numbers that come out just go from 100 down to 0, so the numbers themselves don't matter all that much. This is a list of just the top 20 out of the 38, and we see that num units, according to this, is the most important, followed by the number of units there that have a head of household. I think. I'm not sure what num HH is. We'd have to look at the help file for it. But 100, then 87, then distant. Big drop here. So there you go. Those look like the two most important ones. Now remember, one of the problems with this variable importance is that if there are really important variables that are correlated with one another, they tend to split their importance scores, and you don't get that great of an impression. But hey, this gives at least one opinion here. All right, so part E says that the regularized regression on the scaled and transformed data suggests that alpha equals 1 is the right parameter. Revisit that. Alpha equals 1 is the right parameter here. Now what's cool is that alpha equals 1 is the lasso, and one thing about the lasso is that it actually does automatic feature selection as it's fitting the model. And that means it's able to set coefficients to exactly equal to 0, implying that we've taken them out of the model. So we want to figure out, well, which of these coefficients that are equal to 0 here. So cheat sheet time. I don't remember what this code is. Let's go and take a look at how to do this. So we'll get to this regularized logistic regression. And where's my code that tells us which of these variables don't really matter? I hope this is in the cheat sheet. So we're looking. Look at the coefficient of the selected model to see if any were 0. So let's copy this. Just got to change the name of the data frame that I'm looking at. So this was the coefficients. Long list of coefficients. It's kind of hard to see. Looks like this one coefficient was set to 0. And let's just get the names of these models correct. Here are the ones that were non-zero in this case. So almost everything is non-zero. The ones that are equal to 0, we can scan through this list, and it looks like the only one that was set to 0 was urban. So there we go. Looks like urban we could throw out.